Hello everyone, welcome back to lesson number 29 where we're talking about area between two curves. In the very first video we talked about how we could have a curve where a clear top and a clear bottom, and I didn't spend very much time talking about this, but the rectangle that we'd be creating for this would be vertical. And so what we remember is that we bounded this from A to B, so I really would like these equations to match that. So the area would be the integration from A to B of our top function minus our bottom function. So this integration would be from A to B of f of x minus g of x dx. And so this is what you would do to find that area. And again, I'm so sorry for the handwriting. Well, what if we don't have a clear top and a clear bottom? Like if I were to look at this figure right here, and I want to look at maybe what's going on right here in this rectangle, well, the top and the bottom is actually the same curve. And let's not even get started with the craziness that is like this right here, right? So we can't do that. We can't do that. Well, it would make more sense if we turn our rectangle to make it horizontal, right? And I'm using the rectangle because of, the whole Riemann sum thing that we talked about a long time ago with this. So we can now do this no matter where we put the rectangle in this shape. Our right curve and our left curve are always going to be the same thing, right? So this is always going to be on the right side, our f of x, or f of y and this is going to be our g of y. So I want to say that in the case of this, it's right minus left. So it's going to be the right side minus the left side. And again, we're bounded by our y values. And that's why I believe now that I'm looking at this more, that's why this was marked as x's, because when we're looking at it from top to bottom, it's all about the x. It's all about the x. Well, if we're looking at it from right to left, it's all about the y's. It's all about the y values. So let's look at a couple of examples and see what we can do with them. So if you guys look at example number 5, it says find the area bounded by x equals y squared and then x equals 3y plus 4. Notice that the equation is given to you in terms of x, right? They're telling us here that if we're looking at x equals, and you guys can see this for both the examples on the screen, that we're going to do right minus left. So we still want to graph these things, right? So we want to graph this. Well, x equals y squared. So what some people do is they want to just really quickly take a second and rewrite it back in time of y, right? This would be y equals the square root of plus or minus square root of x. So if I do that, I'm going to go this, and then it's going to be 4, 2, and so it's going to also be down here. So this is what the graph, and again, remember, just like in the previous video, we don't have to have something perfect. We just want to know what the right curve is and what the left curve is. So y equals plus or minus the square root of x, and this right here is going to be 3y is equal to x minus 4, so x is going to be equal to 1/3 x minus 4 over 3. So I'm going to go ahead and draw that one. And again, I know it's about 4/3, so like right here, negative 4/3, and then we're going to go up 1, 1, 2, up 1, 1, 2, 3, up 1, 1, 2, 3, blah, 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 blah. So it's going to look something like this. And I could, if you need me to, I'm going to continue on with my purple curve, because they are going to intersect again. All right, and so we have ourselves a little region here. Now, you're looking at this thinking, okay, this should be maybe a top but this bottom. But again, if you look at what's going on right here, this top curve is your purple, and this bottom curve is going to be our gray. But then if you look over here, and let's get rid of my little shading region for a second here. But if I look at over here, then my left, or my top and my bottom are going to be this purple curve. So we want to shade our region where this is always going to be the right-hand side of our curve, and this is always going to be our left-hand side. So this is going to be the right, and this is going to be the left. So I'm going to go ahead and move our equation stuff up here because we don't really need it anymore, but we'll just keep there as our work. So when we actually solve this problem, we're going to integrate our right function, where our right function is actually going to be our line. So it's going to be 3y plus 4. And we're going to subtract our left function. And our left function is going to be the line, or the curve of x equals y squared. So it's going to be minus y squared. Everything's in terms of y here. Everything's in terms of y here. So we want to make sure we do this. And we would integrate this normally as we would for x as well. And just like previously, guys, we're going to set the two things equal to each other. We're going to set x squared equal to 3y plus 4, and we're going to find out where their intersection points are. And if we just do a quick factoring, and most of the factoring questions are going to be pretty straightforward. And you guys know that clearly this looks like 1 is going to be at y equals 1, right? Y equals -1, I should say. Y equals -1. So this would be negative, this would be plus. So we get y equals 4 and y equals -1. So we're going to integrate this from -1 to +4. And this is the setup that you're going to do for this problem. I just want to clarify something really quickly, ladies and gentlemen, that if you're doing this bounded by x equals functions where we have y's, I always tell students that they want to draw their intersection points like this. Again, this is clearly not the best example because it's going to, my rough sketch is not great because it does intersect at 4 and this does not look like that. But the reason why I'm drawing these lines like this is not really to show you guys where they actually intersect, but to remind you that we're not looking at the x values. That is a classic mistake that students make when they're trying to figure this out. They're going to try to find out this, they're going to use this, and they're going to use this number as the x values. We want the y values. We want the y values for what we're doing right here. Okay, so that's really, really, really important for me to stress with you guys here. When we do integrate this, we get 1/25/6. Like I said, my focus is really not on the actual integration part of it. That's just fundamental thermocalculus. My whole part of this is just to make sure that you guys are comfortable with what we, how we set up the problems. So let me go ahead and just do that. So y equals 4, y equals -1. All right, so let's look at the next one. The next one says, find the area of the region bound by x equals 1 minus y squared, and then the line x equals y minus 1. So just like before, guys, we could do y equals x plus 1, just to get an idea of what the graph looks like. So plus 1, and our slope is 1, so we're just going to do points like this. So this is what our line looks like. Which again, I apologize for not the straightest line here, but it is what it is. Again, I can't stress enough, rough sketch. Now, instead of trying to solve for y here, because if you solve for y, you're going to get y squared equals negative x plus 1. And then you're going to have to figure out, okay, well, this graph for this is going to be plus or minus the square root of negative x plus 1. I think that's silly. I don't think we need to do that at all. This is a much easier way of thinking about how to solve this problem. The first thing that I would strongly suggest that you guys do is before we graph it, and I have not done this at all, but I strongly suggest, and I will do this from every example we do from here on out, is find the intersection points first. I think that's just really helpful to do. So let's go ahead and set these two things equal to each other and solve for it. So again, I'm going to try to make the y squared positive. I'm going to make the y squared positive, and I get -2 here. And so I get that they're intersecting at y equals, let's see, this is 2, this is 1, this is plus, this is minus. So they intersect at y equals -2, and they intersect at +1. So y equals -2, and y equals 1. Okay, so that's really kind of my bound of what I'm looking at. Now looking at this function right here, I can just say right here, y squared equals -x plus 1. Since y squared is negative, then I know that my parabola is going to be opened up on the x-axis, or open it up to the left, right? X squared is positive, it looks like this. Negative x squared, it looks like that. Well, when y is negative, it's going to open up like this. And I know that I have an intercept right here, and let me change the color. I know I have an intercept right here. So when y equals 0, when y equals 0, x is going to be equal to 1. So I know my graph is going to look something like this, right? And I know they're going to intersect here and here. I know these are two solutions to my function because, again, they intersect at these 2 points. So this gives me my region. So the right-hand side is going to be the curve. My left-hand side is going to be the line. So when I'm solving this problem, all I have to do is actually write the integration. And again, it's from -2 to 1. It's the -2, 1. And guys, again, what I was talking about up here is that students are going to look at this and they're going to integrate from, they're going to like, oh, 1, 2, 3, -3 to +1. Because they're going to look at the x values. It's all about the y values here. It's all about y here. What's the lowest y? What's the highest y? So -2 to 1. Again, our right function is going to be 1 minus y squared. This is why it's so important. We're going to subtract. And again, we want to put a parentheses because we want to make sure that we do distribute the negative y plus 1 if we were to do this by hand. Because all these questions can be done easily by hand. So now that you've done that, we would integrate this. We're going to get 4.5. 4.5 for this. And that's going to give us the region of the area between these two curves right here. I do want to show you guys really quickly that yes, you could have done this using x's. And so I'm going to show you guys the answer key that I have up. So is there a wrong way or a right way to do it? Well, no, but there's an easier way versus a hard way. So when you're graphing this, you could, if you wanted to, rewrite these in terms of y, which you can see right here. And then I could see, based on my picture of this, that I do intersect at x equals -3 and then x equals 1. But if you guys look at the problem like this, and like I said, this is just a little me randomly talking here for a second, from -3 to 0, this is your top function and this is your bottom function. So you can do it that way. So you have your top function, which is your line, and then your bottom function is going to be your curve. So you can rewrite that. But from 0 to 1, your top function is the same as your bottom function. And so the only reason I'm showing this to you guys in the video is because I think, again, the blue with respect to the y is so much easier to do. But you could say the top function, which is going to be the positive of negative x plus 1, minus the bottom, which is the negative part of your curve, dx, and you're going to get a value there as well. So when we start talking about other problems, volume, I'm going to show you guys how to do it both ways, but there's usually a better way of doing the problems. And so that's why I just went ahead and showed that to you guys there, that this, what we did, is so much easier to do. All right, guys, and I think this is where it'd be a good stopping point for this video. We're going to come back. I'm going to show you guys a calculator trick and do a couple more examples with area. So I'll see you guys in the third video.